probably our last lecture on Lagrangian mechanics. In the last lecture, we have or rather in the second half of the last lecture, we have started discussion on Lagrangian in an accelerated or non-inertial frame. In the previous class, we have studied what is the form of Lagrangian and the Lagrange's equation of motion when the non-inertial frame is a special type of frame which is moving with respect to an inertial frame with translational acceleration. Today we shall consider another type of non-inertial frame, that is the rotating frame. We consider a frame S with axis XYZ, which is an inertial frame, and another frame S prime with axis X prime Y S prime with axis X prime Y prime Z prime, having the same origin as with this S frame, but it is rotating about the S frame with an angular velocity omega. So S prime is a non-inertial frame. We know that the time derivative in two frames are related by the fact that ddt, the time derivative as viewed of any quantity as viewed in S frame is related to the time derivative as viewed in prime frame via this relation. So we write it that if we write the quantity to be R, then we know the firstly we write it in terms of R, so or we get V, the velocity of a particle as viewed in S frame is V prime, the velocity in prime frame omega cross R. Since both the coordinate system has the same origin, then if we consider any point P, the position vector of the particle can be written as R when viewed in S frame, and it is also R prime. The same R is equal to R prime. Only difference is that when we write R in S frame, it is I cap x plus j cap y plus k cap j, and when we write R prime in prime frame, it is I prime cap plus x prime plus j prime cap y prime plus k prime cap j prime. Only this is the change, so we can write it as v prime plus omega cross R prime as well. And this is the quantity, here P is written in terms of the quantities related to the prime frame. We want to find out the Lagrangian of a particle in prime frame. The Lagrangian being a scalar, its numerical value is the same in both the frames. So what we do, we write Lagrangian in prime frame, and then we change the variables related to the prime frame to get the Lagrangian in a prime frame. That is to say, we write as and for V we write this expression. So this is the Lagrangian is half m. If we write it in component form, we get it is Vx prime plus the x component of this quantity, this is omega yj prime, omega z y prime this quantity square by prime plus y component of this is z prime square plus bz prime plus omega x y prime minus omega y x prime square minus b, and b is a function of x prime, y prime, z prime. So if we want to use Lagrange's equation, then we need to calculate the partial derivatives of L with respect to coordinates and velocities. So first we calculate this quantity del L del x prime. There is a contribution to del x del y prime from this term, and from this term. If we come to this contribution to this term, it is m dy prime this is omega z x prime minus omega x z prime multiplied by omega z, and from this term the contribution is the minus sign will be there because this is vz prime plus omega x y prime minus omega y x prime minus del v del x prime. This is the contribution from this term. You see that you may decouple this thing. This is basically the y component of b prime plus omega cos r prime. This is the y component of this, and this is the z component of b prime plus omega cos r prime. So we write it as m b prime plus omega cos r, its y component, times omega z minus b prime plus omega cos r prime z component into we have forward to write omega y. There is a mistake. Omega y minus del v del x prime. So this is del v del x prime. So this is x component minus del v del x prime. You see, this is the x component of this quantity. Similarly, if you calculate del L del x prime dot, that is del L del Vx prime. Now the Vx prime contribution already is there for this term. So this is M this is our, and this is equal to M V prime plus omega cos r times x component. So if we write, if we combine all these components, then we can write that del L del R del L del R prime, this is equal to, look at this equation, M, we get from this relation, M, this V prime cross omega, V prime cross omega plus omega cross R prime cross omega, and this part is V. And similarly, if we write this term, then we get del L del V prime is equal to M V prime plus omega cross R prime. So if we now apply this to Euler-Lagrange equation, so these are the two relations which we need. So the Euler-Lagrange equation is ddt of del L del V prime minus del L del R prime is equal to 0, or we have ddt of this quantity M V prime plus M omega cos R prime, and we write it on the other side. So this is equal to M V prime cos omega plus M omega cos R prime cos omega minus gradient of V prime. Here we have two terms. One is M dv prime dt. Actually, this time derivative is done in prime term. Here there are two terms. One is M d omega dt cross R prime plus M omega cross V prime. There are two terms. First we have done derivative of this, keeping this fixed, so this is this term, and in the second case we have kept the first vector fixed and derivative of the second. So, and on the other hand side we have M P prime cross omega plus M omega cross R prime cos omega minus the inertia. This term can also be written as grad of V, or we write we take this term on the other side, so we write m r prime cross d omega dt. This term is taken on the other side and we change the ordering, so this is y is m v prime cross omega, the Coriolis force. This is the Euler force, the Coriolis force. This is centrifugal force. This is the inertial force, m dv dt. So we can write the equation of motion in a non-inertial frame, and we identify this is the Euler force, this is the Coriolis force, this is the centrifugal force, and it is the inertial force in S prime, and it is the inertial force in the S prime frame. So this is the relation that we are habituated with. We get the same relation through Lagrangian formalism. There is another mathematically sophisticated way of arriving at the relation. Let me also describe this. The Lagrangian we have written as L prime, as we have done in this first part, is half m p prime plus omega cross r prime square minus b. So this we wrote as p prime square, which we write v prime dot v prime plus the cross term is twice v prime dot omega cross r prime plus omega cos r prime dot r prime minus b. We take a differential or a change in Lagrangian. That means that Lagrangian was L prime with r prime and b prime. Now the Lagrangian changes to L prime plus gl prime when r prime change is equal to r prime plus gr prime, and b prime is there is b prime, and obviously t is there. So what is the change? This change dl prime will be something into dot dr prime, some vector times dr prime plus something dot dv prime. This is the main spirit of such calculation. So we write the differential of it. So dl prime is equal to, from first term it is m v prime dot dv prime. This differential is taken in prime frame. So in prime frame, omega is a constant vector. Keep it in mind. So come to this term. These two cancels out, and this can be written as m omega cross r prime dot dv prime, and again it can be written as m v prime dot omega cross dr prime. This is the two term originating from there, and there is a term omega cross r prime dot omega dot dr prime. There are two such terms, one coming from this, another coming from this, which are just the half factor, and this part is written as grad v dot dr prime. So let me rearrange the terms. First term, m v prime dot dv prime. This is the contribution of this term. There is another contribution to this. This is m omega cross r prime dot dv prime. This is the contribution from all dv prime. There are dr prime dependent terms. So this, let me consider dr prime term. We write it as m v prime cross omega dot dr prime. This is a scalar triple product. So keeping the ordering fixed, we have just interchanged the dot and cross positions of dot and cross. And this term we write it as m omega cross r prime cross omega dot r prime. This part is so that we write del L del R prime. Del L del R prime is the contribution from here and from there. So it is M omega and del L del V prime is equal to M V prime plus M. This is the same equation as we obtained earlier. So we can now fit these two equations to Euler Lagrange equation, and we get the same equation as we have obtained just a few minutes back when we performed the calculation explicitly in component forms. And this is in this case we have performed the calculation in a bit sophisticated way using the vector relations. This is the relation. This type of calculation is done in the book of Landau lift switch, in the classical mechanics book of Landau lift switch.